Okay, great. Yeah, I'm excited to be here. It's really a wonderful conference, and yeah, I'm excited here to give the first talk in the quantum communications network session and share with you my vision of a quantum network where the nodes actually consist of atomic arrays, so the kind of arrays that Misha Lukin talked about, atoms and optical tweezers that can then be coupled to optical interfaces to distribute entanglement over long distances. But before I go into the details, let's actually zoom out and ask, okay, what is a quantum network good for? The first thing that maybe comes to mind is securely communicating over long distances, QKD. And yeah, if you really want to go long distances, you actually would want something like a quantum repeater in between to be able to basically swap entanglement over large distances. And there's much more to a quantum network. I think there's a very compelling argument to make that a quantum network or the modularity that a quantum network offers will be needed to actually scale quantum information processors. I think no matter what the architecture is, if it's superconducting qubits, neutral atoms or trapped ions, at some point you're going to run out of space in your cryostat, under your microscope, on your trapped ion chip, and you want some way to link modules together, and a quantum network can do that. And another really compelling application would be quantum sensing with distributed nodes, for instance, distributed clocks, as was suggested here, or maybe even using a quantum network to enhance the enhanced telescopes looking at faint objects. And these are just some of the applications for quantum networks. So let's dig a little bit deeper and work out what the requirements of a quantum network are. So here's just a little cartoon, quantum network nodes over some macroscopic distance with some quantum repeaters in between. So now if you think about maybe a task you would want to do, you want to distribute entanglement between these distant network nodes over a quantum repeater. So you have like one quantum processing unit at Alice, one at Bob, and in between a repeater. Okay, you first have to establish entanglement between the nodes and the repeater. Maybe you want to do a little bit of purification to have high fidelity entanglement that you can then swap to the nodes and then maybe perform a gate teleportation between communication and data qubits. Now there's actually quite a bit happening here. And yeah, if you think about it, these nodes, they should be quite powerful. You should have multiple qubits at each nodes. Inside the nodes, you should be able to process. You need long coherence time, high fidelity gates, measurements, and then you also need these optical interfaces to distribute entanglement. That's a pretty long wish list. So what is the current state of quantum networks? I tried to summarize the current state in this plot here. It's kind of busy, but let me walk you through it. Here on the x-axis, you see the distance between two nodes, each node hosting a qubit, a meta qubit, and then here on the y-axis you see the link efficiency, and this is a figure of merit that's basically the product of the coherence time times the entanglement rate. Basically, you would maybe want in a network to be able to distribute entanglement faster than information decoheres at the nodes. So ideally, we would want to be above 1 with this link efficiency, and ideally, you would also want to go very far distance, but there's actually quite an empty spot up here. So yeah, of course, as the distance goes up, photons get lost, your entanglement rate goes down, and this link efficiency goes down. Another takeaway from this plot is actually that quantum networks is a really exciting field to work in. You see there are many different platforms that have done distributed entanglement and V-centers, ions, neutral atoms, silicon vacancy, quantum dots, now even rare earth ions also in crystals. And there's a second maybe takeaway is all of these experiments, they were just performed between two nodes. And I think that really characterizes the state of the art. It's still kind of prototype networks with a single qubit at each node and then two of these nodes. There's one exception to that. There's a very nice 3-node experiment, but this is really state of the art that you have two mainly nodes, maybe 3 nodes. So we are not quite there where we would want to be with the networks. Parallel to these developments, also, we have seen the rise of these atom arrays. So Misha Lukin talked about it, and we heard it multiple times. So the ability to trap single atoms using optical tweezers is really compelling because, you can trap many atoms Here's a nice result from Manuel Andres' group at Caltech, where they trapped more than 6,000 atoms that are highly coherent. They are all very long-lived qubit states. They are all indistinguishable, which is really important for quantum networks. And then you can perform these coherent operations. You can perform 2-qubit gates using these Rydberg states. And now we see that people use that to really compile circuits on these atom arrays, that these 2-qubit gate fidelities are just getting better and better. And okay, then these, of course, really wonderful results of this logical qubit performance in Misha Lukin's group. At the same time, I think atoms are also amazing because, okay, they emit light, and I can use that to make an optical interface. Here, for instance, from Gerhard Rempel's group, distributing entanglement between 2 atoms in an optical cavity. But these experiments, they're still kind of limited to maybe 1 or 2 atoms. So my idea, and it's not my idea, I think a compelling idea is to somehow combine now these atomic arrays with optical interfaces. And basically the 2 architectures that come to mind is here, for instance, this is kind of an architecture paper from Mark Safman's group, where you would have these macroscopic cavities and you put an atomic array inside. And then another way of doing it is that you actually use very microscopic cavities, nano-photonic crystal cavities, for instance, and that you basically have arrays from which you then grab atoms and couple on these nano-photonic crystals to realize this optical interface. And this is actually the architecture that we are working on and that I want to tell you more about. So in my talk, I'm going to tell you how to combine now atom arrays with these nano-photonic chips that actually host many of these nano-photonic crystal cavities. And then, okay, there's a second part of the talk where I maybe do a little jump and also tell you very briefly about like a second set of experiments that is more about the inner node processing in these nodes. Okay, so let's get started. So how do you combine atoms with nanophotonics? Okay, you have your atom, you have that in an optical tweezer. And then you have the nanophotonics, of course, with all their nice properties. You can confine light very tightly. These are very small mode volume optical cavities, which can give you very strong coupling when you place the atom on top of this cavity. So you basically just take the optical tweezer, put it on top of the cavity, and then you evanescently couple to this optical mode. Here's an example where we have done that. This was during my postdoc, where we took a single rubidium atom, put it on a nanophotonic crystal cavity, and then you can see how a single atom, for instance, changes the reflectivity of a cavity. Okay, this is just like theory, empty cavity, you get this reflection, and then if a single atom's coupled strongly, it should be able to basically break this resonance. And this is exactly what we see here, single rubidium atom coupled to the cavity. And from basically the spectrum and the width of this, you can get the cooperativity, basically the figure of merit, how strong this coupling is, comparing the coupling strength to the decay rates, and this can be many tens cooperativity. Now, this is really compelling, but if you wanted to use this in a quantum network, okay, there's maybe one downside. These photons that are emitted there in the infrared. If you're really serious about quantum networks over long distances, there's actually no way around working at telecom wavelength where you can get optical fibers that have very low loss. So you don't want to sit over here in the infrared, you want to sit either here or here to get these low loss fibers. And okay, there's several ways of getting there. One would be to just take what you have, maybe take your atom, take the infrared emission, and then convert it in a quantum frequency converter, as was done in Harald Weinfurter's group, and then distribute it. That's interesting. And of course, it adds some noise, it adds some complexity, and also some inefficiencies. That's why maybe a second strategy where you actually directly get telecom photons from the atoms would be really compelling. But actually atoms, at least atoms that you can conveniently trap and manipulate, they don't emit telecom photons from the ground state. But actually if you increase your search radius and you also allow yourself to work with excited states, you can find very nice telecom transition basically for any atom. So this is for cesium, the same works for rubidium, works basically for any atom. And our question was, okay, how do we get these telecom photons out and combine them with the very nice long-lived qubit states in the ground state? And here's a protocol that we came up with. So you have the long-lived qubit states, and here's a simplified level diagram. You have your telecom transition, and that is where you put now a cavity. And then basically, your target state that you want to create is an atom-photon entangled state where the atom is entangled with the emission time of the photon either being emitted early or late, or actually end late, because it's a coherent superposition. And the way you do it is basically you start in the superposition of these qubit states, you take then the 0 part on a little round trip, you get 1/2 photon out, and then you flip around this 0 and 1 and you do a second round trip and you get the second half at a later time. So we analyze this kind of round trip. Here you do short pulses, these are the optical pulses, and here you see the populations as they evolve, as you travel through. The details are not so important. You start in the ground state here in blue, you go on a round trip and you come back. And of course there are some decays and some infidelities, but we analyze this error, and of course the error scales with how strongly you can couple. And we expect that we can couple also with these tens of cooperativity, maybe 100, and then you can get the error down to percentage levels. So this would be really, really compelling, and this really compelled us to actually make this a reality. So we fabricate these nano-photonic chips. So the nice thing here, you really see we have many of these cavities. They are all at the telecom wavelengths. Now this is optimized for cesium, and we get very nice quality factors from which we would expect very high cooperativities. Another kind of technical question is, okay, how do you get light in and out of these cavities? Previously, maybe some groups have attached fibers to these cavities or maybe approached them with lensed fibers. Here, actually, what we do, we just couple to these cavities in free space. So we have optimized here basically the outcouplers of these cavities to exactly match the incoupling mode of our objective. So this is just simulation of, okay, what comes out of the waveguide and what is maybe the coupling mode of our objective. And then the overlap of this can be up to 90% and higher. Of course, these are nice numerical simulation. They always look nice and you get nice numbers out. But so we wanted to test this. So here you see our photonic chip. This is the coupling objective. These nano-photonic crystal cavities, they hang off to the edge of the chip. And then we couple into these, and okay, this was just, we didn't really optimize this, but we get about 60% coupling efficiency. So this is actually really fantastic because it saves you lots of complexity. You don't have to have any coupling mechanism in your vacuum chamber. And just from the outside with your objective, you can choose which cavity you work with, or you can even work with multiple cavities at the same time. So now let's put it all together. So this is schematically what the setup looks like. It's just a vacuum chamber, and then we have all the kind of atom array technology that you expect, acousto-optic deflectors, cameras, and here we have our coupling objective, and we have the chip inside. This is actually what it looks in reality, so it's a nice small chamber, and the special thing is inside we have this chip. And okay, this chip is basically semi-open, so we get all the cooling light in, the objectives in here, and with the free space coupling we get the light out of the chip. Okay, now let's do experiments. Okay, we have the chip inside, and of course we want to put atoms on it, but okay, there are a few problems. Not everything that you do with atom arrays normally in an empty vacuum chamber works also with this nano-photonic chip. For instance, if you now want to image the atoms, see where the atoms are, you typically would excite the atoms and collect the fluorescence, and you excite it maybe from different directions than from where you are looking, so you just see the scattered light. But here actually, because of the nanophotonic structures, there are a lot of scatterers, and you would basically just see a camera image like this. So you would be completely blinded by the light that is scattered from the excitation laser from the chip. So we had to solve this problem, and the way we solved it is actually by using kind of the excitation scheme that we will later use for entanglement. And what we do here is we excite to these higher states from where we get telecom emission, but we also get infrared emission that is at a different wavelength from where we excite. And then we can actually spectrally separate these two wavelengths, and then we can actually see single atoms on top of all the scattered light. So this is all the scattered light at 850, and here's the single atom fluorescence at 895. So a very clear single shot, single atom image in very similar times than what you would do in an atom array. So this is a very nice method. We can actually put a whole array next to the chip or even like interleave it with the chip. So these things actually work very nicely. We can cool the atoms, image the atoms, and now we kind of move on top of the chip. So we can even image the atoms when they are on top of the nanophotonic crystal cavities here. And of course, here you just see an XY that they are on top of each other. The important thing is now, do they also sit close to the surface? And as you put the tweezer on top of this nano-photonic crystal cavity, actually some of the tweezer light will reflect. It will form a standing wave, and your goal is to get into this first antinode here. And to verify that we can actually do that, we look at the light shift that the light puts on the atom, and here we see atoms that we scan across these cavities, and every time we hit the cavity, you see this light shift go up. And from the strength of the shift, we see that the atoms are loaded a few hundred nanometers above the device where we would expect a strong coupling. Here's another kind of thing that typically atom arrays do. The loading into these optical tweezers is probabilistic, so sometimes you have an atom, sometimes don't. So what you want to do is you want to take an image, first image. Okay, here it's a bit noisy, but you see 4 atoms, and then we grab these 4 atoms and put on these 4 cavities. So this is this atom rearrangement that kind of has propelled the field, but here rearrangement on top of the devices. And you could imagine now, as you have multiple of these optical interfaces, you could, for instance, use that to speed up your entanglement rates between the nodes, basically by trying entanglement in parallel and multiplexing, basically giving you an n boost, where n is the number of atoms. And then the second thing we did is we trapped probabilistically atoms, and then we rearranged them on the same device. And this is kind of, okay, not what we are right now pursuing, but maybe in the future, where you can take an array of atoms, put it on a nano-photonic device, and then actually use the photon-mediated interactions to study interesting many-body physics on these devices, in the spirit of Jeff Kimball in his previous work at Caltech. So this is really exciting, and of course I would love to show you entanglement right now. But okay, what actually the chip I showed you before in the vacuum chamber was not on resonance with the atoms exactly yet. Now we found a new device and a way to tune the chip on top of the resonance with the atoms by basically heating it locally with a laser. So now we are sitting at this point, and we are looking for the strong coupling of the atom and the cavity. So this is our kind of network efforts with the nano-photonics. Now I want to switch gears a tiny bit. Do I still have 5 minutes? Yeah, super. And talk about kind of the inner node processing that you could do. And in particular, what we have is a dual species array. So our atoms arrays, they are a bit different. We have 2 types of atoms. And why do we do that? It's basically, you can set apart 2 different functions for these atoms. In a network setting, one could be a communication qubit, one could be a data qubit. And in many other instances for quantum error correction, maybe one could be your ancilla syndrome qubits and the other one your data qubits. So we have these large arrays with 500 sites here of single rubidium and cesium atoms. And just to show you some results that we got on this, here's a nice one from last year where we set 2 different tasks for the atoms. One is the data atom, and the other atom is actually, we call it a spectator qubit, or the community calls it a spectator qubit, basically a sensor that senses noise in the background that could affect your data qubits. So you have a co-localized sensor in your chip, in your quantum processor, and if you can sense the noise in real time, you have the ability to correct for it in real time if the noise is correlated between your sensor and your data qubit. And I'm just flashing this here. So we have the data qubit, we injected some magnetic field noise, and then we looked at, okay, what is the coherence of the data qubit? So here you would expect some oscillation, but it's completely flat because of the noise. But then if we measure the noise, calculate in real time what the effect is on the data qubits, we can actually adjust here this phase. And then, here's the sequence. We do a mid-circuit readout, we analyze it, and then adjust the phase, and then we can regain this coherence. So this is not like quantum error correction, how you think about it, but it's a sort of error correction for these correlated phase errors, and that works really nicely. And now, just the final thing, okay, I will show you entanglement, but not entanglement between nodes, but entanglement between now these atoms. So here we now also use these Rydberg excitations, and the story about Rydberg, just like Misha told, it doesn't really change in a dual species. You excite the atoms to Rydberg states, you get this massively enhanced Rydberg interactions, and we can now, because of the spectral selectivity, excite both or only one of them, and then we get interactions. We get interactions between the atoms, so here's one color missing. Purple is somehow missing. That would be here. So we can get interactions that are very similar between the species and within one species. basically by choosing which state you work with, which you can freely choose now, you could choose 2 times maybe the 68S state. Every interaction would be very similar. But the nice thing is you can freely choose also different states. And okay, this is now a pity because here you would see a curve that actually kind of really extends here on this logarithmic plot, where now the interspecies interactions can be strongly enhanced. So you can get maybe orders of magnitude stronger interaction between the species because of so-called Förster resonances that you can nicely tune and find between the species. So, and this is a really interesting regime because here you could use one atom to control many around them. You could do native multi-qubit gates and also stabilizer measurements very nicely. So let me just show you what we did there. So here now we have the atoms, the ground state and the Rydberg state. And the first thing we looked for is Rydberg blockade. So can one atom in the Rydberg state blockade the dynamics of the other? And this is exactly what we see. So this is cesium-Rabi oscillation between ground Rydberg state. And here is the blockaded Rabi oscillation when we put the rubidium atom in a Rydberg state. And then with this conditional evolution, you can implement a gate between these hyperfine qubits. Okay, you basically do this pi, 2 pi, pi scheme, or this is what we did, where you have a conditional evolution of the atom that depends on the state of the control atom. And here we exactly see this conditional phase that is imprinted on the rubidium atom by the state of the cesium atom. And okay, with that you can make entanglement. Just like future directions that we want to do with this dual species architecture, we really like this asymmetric interaction regime, and we can use it to generate large entangled states. It's also very useful to generate cluster states. And then, okay, we are interested in error correction, and in particular the fact that now with these asymmetric interactions you have native multi-qubit gates that can very nicely help you to extract syndromes, and now you have the nice readout on the other species. But I also in kind of the many-body regime, I think there's a lot of nice new things to explore. Basically, you have 2 spin Hamiltonians on the 2 species with tunable coupling. And yeah, we are also thinking about here nice quantum simulation. And ultimately, I want to combine these 2 efforts, these dual species arrays with the photonic interfaces for these integrated networks with these processing nodes. So with that, I thank you very much. I thank my wonderful group. And please, if you have any questions, let me know.
Thank you for this wonderful presentation. We have time for questions. There's the first one over there. Do we have a microphone also?
Okay, hello. So my question is, how do you image the 2 species? Do you use 2 cameras separated by diacritics or separated in time, or what technique?
We could use 2 cameras, but we just use one, and these arrays, they are interleaved. But I mean, depending if we shine in rubidium lasers, then we get rubidium fluorescence or cesium fluorescence. We can do it at the same time. I think here we do it actually interleaved. Yeah.
There's another question over there.
So thanks for the nice talk. Regarding the cavities, did you undercut them or remove the thing for coupling? And how reliably does this work for you?
Wow, okay. So you're doing fab?
Personal problems, let's say it that way.
I mean, we do undercut it. So here we do like a combination of, okay, we first fabricate the devices in the middle of the chip, then we kind of dice it, and then we do KOH etching to make them freestanding. So this is silicon nitride. So with KOH and the selectivity, you can take this away, and this is about like, it's like 300 micrometers thick. So it actually works quite nice.
All right, thanks. So, but you don't see that, you don't see any bending or so of your freestanding structures?
No, we don't see any. I mean, maybe you can, there's a tiny bend or so, but this works well. The only thing that's a little bit tricky, where you have to kind of in real time check a bit, if you etch too far, okay, then you etch here and then they kind of collapse and fall down. But
all right. Thanks.
Yeah.
On about the same part of your talk. So you showed how to do a coupling between an atomic qubit and a photon. And so maybe you want to make a link with this along the lines of Chris Monroe and so forth.
Exactly.
So what results do you have in this regard? Do you have a entanglement generation rate for a certain distance that you can present?
So what results do I have? I don't have experimental results where we have created entanglement between two distant nodes. I have lots of calculations and entanglement rates, but okay, right now we are really at this step of having the cavity on resonance and now coupling to the cavity. Yes.
And is this on your roadmap, these?
Yes, absolutely. Yeah. Absolutely. So, so we already have all the pulse sequences to generate locally entanglement of the atom and the photon. And then, okay, we are going to use exactly kind of an entanglement swapping protocol where we interfere the photons on the beam splitter.
Thank you.
Okay, there's a question in the back.
Thanks. Yes, very nice talk. Thanks a lot. How long can you keep those atoms you trap in the tweezer over those waveguides? How long can you keep them there?
Yeah, great question. Sorry, I don't have the data here. We can keep them for about a second. And then when we keep them off the chip, we see about between 10 and 30 seconds or so. So the lifetime goes a bit down. Probably there's a bit more heating or so. But okay, a second is actually plenty on kind of what we envision an entanglement protocol takes. Yeah.
Okay, thanks.
Okay, so in view of time, let's move on to the next speaker and thank Hannes again for his very nice talk.